Yesterday, we started off by learning two new terms. They were mass defect and binding energy. And we learned those two new terms in the context of two nuclear processes, nuclear fusion and nuclear fission. Nuclear fission, you remember, is the process whereby a heavy nucleus splits up into two or more lighter nuclei. We get some neutrons in there as well, but if we ignore those just for a second, we always start off with something that's heavy, and we end up with a couple of things that are lighter. Nuclear fusion is the exact opposite. We start off, if we pretend there's no neutrons for just a second, we start off with a couple, two light things, and end up with one heavier thing. For instance, hydrogen 2 and hydrogen 2 form helium 3, plus a bunch of energy that's produced as well. Right? Where does that energy come from? Where does the energy come from in a nuclear reaction, any nuclear reaction? The mass defect. What's the mass defect? Well, we defined it in two ways. I'm going to reverse the order of my definitions today. It doesn't really matter. The only reason I'm going to do that is because the first one that we learned yesterday really comes from the second one. So I'm going to list the second one first, that's all. Okay, the second one is the difference in mass. The difference in mass between what? Between what? Good, the nucleus and the nucleons. What's a nucleon? Proton and neutron. It's the parts that make up the nucleus. If we add up the mass of the protons, add up the mass of the neutrons, we get a total for it, and take a look at the mass of the nucleus itself, we're going to find that every single time the mass of the nucleus itself is slightly less than the mass of just all the protons added up and all the neutrons added up. The difference in mass is called the mass defect. Now, that results in a difference in mass between the products and the reactants. Okay, it results in losing mass in a nuclear reaction. I use that term products and reactants. I use that loosely because that's a chemical reaction term, right? Products and reactants. Just that, over the last couple of days, okay, I'm kind of finding that I use that term sometimes not even thinking, and I find that a lot of people this morning were using that term just kind of automatically using that term because that's what they're used to. It doesn't really matter what you call them. Okay, just be familiar with the real terms. Okay, the parent nuclei and the daughter nuclei. Okay, the parent are what we start with. Okay, that would be the reactants, and the daughter nuclei would be what we end up with. So the difference in mass between the products and reactants, or the difference in mass between the daughter nuclei and the parent nuclei. Now, this mass defect gets translated into what we call the binding energy, and there's a few ways that we can define binding energy as well. Okay, the one way that concerns us, the one way that's relevant to us, is the energy that's released in the nuclear reaction, in the fission reaction, in the fusion reaction, in whatever reaction. How are we going to find the value of that binding energy, the energy that's released in the reaction? E is equal to mc squared, m being the mass defect in kilograms, c being the speed of light, 3 times 10 to the 8 meters per second. Somebody this morning said, they didn't convert the mass to kilograms. He used, I forget what units he used, and then he used some constant, okay, that was in the textbook. And he said, well, can I use that? You get me the right answer. I'm like, yeah, you can. Okay, you can. But my suggestion is not to. Okay, there's a reason why. There's a few ways that we can find it, given different units, okay, given different values. But there's one main reason why I don't like you doing that. Okay, it gets confusing. Sometimes, if we go to kilograms always, and the speed of light in meters per second always, then sometimes it takes us 30 extra seconds to do a unit conversion in there. If we took a shortcut, it might take us a few less seconds to do the question. But the more things we learn, the more ways we learn, especially strange terms in strange units, and that's what we'd be dealing with here, okay, the more chance we have of making a silly mistake. Okay, so I'm not going to go that way at all. Okay, if you happen to spot that in your textbook and you want to use it, you go ahead, but use it at your own risk. Okay, because there's a good chance, I think, that you might mess up on it if you do that. So we're always going to go with kilograms, and we're always going to go with C in meters per second. All right. We had 3 questions for homework last night. I want to look at question number 2 and question number 3. If we go over number 3, I'm pretty sure you should be good at number 1, right? Because it's the same question, really, right? Different numbers and stuff, but same idea. Question number 2 is a little bit different because we have to balance it here. Let's do question number 2 first. It says uranium-235 which has an atomic number of 92. How do we find that out? Because it doesn't tell us there. Now, it does tell us, I guess, in question number 1 that it has an atomic number of 92. Okay, but let's say question 1 wasn't there. How would I have gotten that number? Periodic table. It says it absorbs a neutron. So it absorbs a neutron. It actually becomes, for a brief moment in time, uranium-236, right? And then splits up into the bromine and the lanthanum. We're not going to write in that second step, that intermediate step. It's there, but in the end, we want what we end up with. So what do we end up with? Bromine 87 plus lanthanum 146 plus some neutrons and some energy in there as well. We want to figure out how many neutrons we need in order to balance this reaction out. On the left-hand side, we have 236 and 92. On the right-hand side, we've got 86 and 146 is 233. And 35 and 57 is going to give me 92. So how many neutrons are we missing then? 3. Now what we don't want to write is 30N, because that's inferring some kind of nucleus that has 3 neutrons and no protons, 3 neutrons that are together. Okay, that's not what happens. We got 3 neutrons, but they're separate from one another. So we're going to write out 10, the symbol for a neutron. 10, yeah, you're right, thank you. And then put a coefficient of 3 in front of it. So it's going to look like this. Now, I think every example that we've done so far has had 3 neutrons, right? Do they all have 3 neutrons? No, it just happens that all the examples that we've done so far have. There's a question that we're going to do a little bit later today. I forget the number that it is, but it's not 3. Okay, it's 2 or 4 or something like that. So just be prepared for that. All right, now we want to find out how much energy is released in that equation or in that reaction. Hopefully you guys will all have these numbers written down so we don't have to keep going back to the table. What's the mass in atomic mass units of uranium-235? Now, if we've already got that number in kilograms, then go with that. Go with kilograms. If you don't have it in kilograms, then that's okay. It just means a tiny bit of extra work down the road. What's the mass of a neutron? Well, now let's look at bromine 87. And the mass of that one is going to be 86 point. Thank you. Lanthanum 146. And 3 neutrons is going to be 3 times 1.008665 atomic mass units. All right, let's get the mass of what we end up with on the right-hand side. Let's get the mass of what we started with on the left-hand side. And then let's find the mass defect. What is this total mass, by the way? Say that again. Thank you. And on the right-hand side, what would we expect to get? Something that's slightly bigger or something that's slightly smaller? Smaller, probably, yeah. So what do we get there? 230. 872,497. Thank you. Now, we are going to get a number that's smaller. Every single time, we're going to get a number that's slightly smaller. Okay? If we don't, then we've either done it wrong or it's a reaction that can't actually take place, right? Because if it can take place, you have to get a number that's smaller on the right-hand side. But it's not going to be very much smaller. One of the common mistakes that people would make with this would be forgetting to multiply this 1.008 times 3. If you didn't do that, then you'd end up with something like 233 point something. That's too small. It's smaller than 236. It's too much too small. Smaller than 236. So if you get a number that's not real close, then double check your work, okay? All right, now what do we do? MD stands for mass defect. We get that by subtracting these two numbers. And what do we end up getting here? 0.180092. 98, thank you. Atomic mass units again. You guys are much better at subtracting than period 1, by the way. We spent 5 minutes of arguing about what this number minus this number is in period 1. You guys all agree with that, by the way? I hesitate to ask you that question because that's what I said this morning, and then it led to 5 minutes of, no, that's not what it is. Finally, I said, just take the numbers and punch them into your calculator and subtract them. It's not that hard. All right, mass defect is this. We want to do what to that mass defect? What do we got to do to that mass defect? Convert it to kilograms. So let's say 1 atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms is equal to 0.180098. Would you expect to get less than this in kilograms or more than this in kilograms? Should be less, right? Because you have about 1/5 of an atomic mass unit, so it's going to be about 1/5 of the mass in kilograms. What does that work out to be? About 1/5 of this, right? $2.989. Let's keep going. 6268 times 10 to the minus 28. Okay, thank you. Now, if you were to skip the step, okay, or sorry, if you were to take a shortcut, go to your textbook, there is a way to avoid doing this conversion right there. Okay, but that's all it saves, is that conversion right there. Okay, to me, we're better off just doing that conversion and doing it the same way every time, in the same units every time, as opposed to trying to go with an alternate set of units and getting confused about when we can do that and when we can't. So again, to me, just do this. Well, now let's find the energy that's released now, which is of course what we want here. E is equal to mc squared, 2.9896268 times 10 to the minus 28 kilograms. And we multiply that by 3 times 10 to the 8. Don't forget to square that. What do we end up getting there? It's not 167.8, I'll tell you that now. What is it? Someone's going to have that. It's going to be in joules, though, right? 2.69 times 10 to the minus 11 joules. Okay, so I said it wasn't going to be 167.8 because we get the answer in joules. Now, I'm fine with that. I'm fine with you getting it in joules. But if this is an exam and you got 4 options and they're all in mega electron volts, then we have to be able to convert to mega electron volts. So let's say 1 electron volt is 2.69 times 10 to the minus 11 joules. X electron volts, no, that's not right. 1.6 times 10 to the minus 19 joules equals X electron volts over 2.69 times 10 to the minus 11. We solve for X, it works out to be, I believe it's going to be, hold on for a sec, 1.68 times 10 to the 8. 1.68 times 10 to the 8 electron volts. Now, they want it mega electron volts. Let's take off a 10 to the 6, because that's a mega, right? If you take off a 10 to the 6, what do you end up with? 10 to the 2. So we're just replacing a 10 to the 6 with an M, right? So it becomes 1.68 times 10 to the 2 mega electron volts, or 168, which is what they have there. I guess they went 4 digits, right? We should actually, with the way that we did it, we should go 3 digits, right? Because we use this constant right there of 3 digits. Okay, I think they did it a different way, which meant they didn't need to use that number. Sorry. Is that right? Okay. In all likelihood, that's because of them doing it slightly different way. Of course, we should get the same answer either way, right? But sometimes the constants are rounded numbers. And if they use one constant for one set of units and we use a different constant for another set of units, and sometimes we end up with something slightly different. Kind of like with those 2 values of Planck's constant, right? A few times we ended up with a different answer, slightly different. So either way, we're good there. Good? Okay, let's take a quick look at this one together, okay? 1939, 4 German scientists made an important discovery. Kind of ironic, isn't it? Well, because it was, I know it was, I know. Because it was the Americans that developed the nuclear weapon, right? Well, the Germans stopped their program, I think, before they ever developed it. Einstein wrote a letter to Roosevelt that said basically, like, if you don't do this, if you don't get this nuclear weapon designed, then the Germans are going to get it first, and then watch out. So as it turned out, Germany became a non-factor in the nuclear part of the war. But I just found it kind of ironic that it's the Germans that actually discovered the science behind it, and the Americans that used the science to actually use it and win the war. So they made an important discovery. They found that uranium, after absorbing a neutron, splits up into two fragments that each have a smaller mass. Okay, process is known as nuclear fission. We knew that, right? They didn't need to tell us that that process is nuclear fission. There's many possible reactions, two of which are indicated below. They've got a neutron plus uranium-235. Okay, good. Goes to uranium-236. Goes to krypton and barium. This is the example that we gave in your notes, except that they're showing that interim step, right? That intermediate step, where the neutron is absorbed by uranium-235. Doesn't really matter. The next one, almost the same, except this time the two products that the uranium-236 is breaking down into are different. Instead of barium and krypton, it's xenon and strontium. We want to find out the number of neutrons there. So let's figure that out. On the left-hand side, we have 236 and 92. They do me a bit of a favor here. It's a small one, but they don't ask me to add up 1 plus 235, 0 plus 92. They've already done it for me. Although in the end, that's not saving very much time, but something at least. On the right-hand side, 140 plus 92 is going to give me 232. 54 plus 38 is going to give me 92. How many neutrons am I missing? We're missing 4, right? 232 plus 4 neutrons is going to give me 236. So the answer would be A. First time we've seen one where it's not 3 neutrons. Okay, I told you, be prepared for that. Most times it seems to be 3 neutrons, but it can be something else as well. 2 more questions. I'm going to ask you to do these ones yourselves. Okay, we'll give you about 2 minutes to see what you can do with these ones, okay? All right, everyone, let's take a look. It says, the info says, the measurements given below indicate that uranium-235 nucleus has a smaller mass than the mass of the corresponding number of free protons and neutrons. We expect that, right? We know that, okay? We know that that's called the mass defect. If you add up the mass of all the protons and the neutrons that exist inside the nucleus, it's more than the mass of the nucleus itself. So let's get the mass defect now. How are we going to get the mass defect? Well, we know that uranium-235 has this mass, right? The mass of the proton is 1.67. The mass of the neutron is 1.67, a little bit more, right? So what do? Add these two guys up and then subtract it from this? No, not quite. You're on the right track, but not quite. What's the problem with that? Yeah, there's 92 protons here. It's not 1 proton and 1 neutron. You can't add up the mass of a proton and a neutron and expect to get a mass that's bigger than the mass of uranium-235. Okay, it's going to be way less than the mass of uranium-235. You've got to add up the mass of 92 protons and 143 neutrons in order to get the total mass there. What does that work out to be if I multiply these two, and then add them up? I'm going to say 3.9 something, a little bit more than 3.9021. 899 times 10 to the negative 25 kilograms. Does it make sense to everybody what I've done there? How we've got that number? Sorry, go ahead. Had to multiply 1 by 143 here because in a uranium-235 nucleus, there's 92 protons and 235 minus 92 neutrons. So it's going to be 143 neutrons. If I want to find out the total mass of all the protons and neutrons combined, then I've got to multiply each of those by 92 or 143. So mass defect, we're just going to subtract them now. What do we end up getting when we subtract those two numbers? 3.93 minus 3.90. 3.97, sorry? 179. Times 10 to the 3.1799 times 10 to the minus 27 kilograms. How would I express that as B times 10 to the negative W? 3.18, right? If it was AB decimal negative CD, then it would be 3227. Okay, but they're just looking for the base there, B, so it's 3.18 to 3 digits. Right? It always tells you how many digits. So if you're ever puzzled by that, just look, because it always tells you. Now, the nuclear binding energy of uranium-235, this is the easy question. All we have to do is take the number that we just found, although we should use the unrounded number, and say E is equal to mc squared. 3.1799 times 10 to the minus 27 times 3 times 10 to the 8 squared. What do we get there? (2.86 times 10 to the negative 10 joules. They want the answer in electron volts, so you got to do the conversion, right? So you're going to get the number of electron volts there and then plug it in right there. The bad news for this question, sorry, the good news for this question, you're not going to see a situation where you have these two questions together, because they no longer put questions on the exam that are dependent upon the previous question. So if you get the wrong answer for one question, it's not going to affect you for the next question. It used to happen, doesn't happen anymore. Okay, that's the good news. The bad news is, I don't actually think it's that hard. Okay? If we've got the concept down, I don't think it's that hard. Okay, the chances of you getting a question like this, okay, could happen. The chances of you getting a question like this could happen. You probably just won't see them both together, because it would depend upon the previous answer, and that's not going to happen. Okay, let's spend a few minutes just reviewing Rutherford and Bohr that we talked about yesterday, and then we'll extend to Bohr a little bit, and then we'll finish it up. Gold foil experiment, sometimes they call it the alpha scattering experiment. Basically, we've got these alpha particles being emitted from some kind of radioactive material inside this box. We've got this thin layer of gold foil, and then we've got this phosphorescent screen called a scintillation screen that glows when struck by these moving charged particles, by these alpha particles. Now, Rutherford and his assistants noticed three things as they fired these alpha particles one at a time at this gold foil. They noticed that most of these alpha particles did what? They went straight through. Most of the alpha particles went straight through. And what did that tell us? What did that tell these guys 100 years ago-ish? Yeah, most of the atom is empty space. Okay, we used the analogy yesterday of the football field in the middle of a 110,000 seat stadium. Okay, if you put a dime in the middle of the football field and the rest of the stadium was the rest of the atom, the dime would actually be a little bit too big to be your nucleus. Okay, that's how small the nucleus is compared to the empty space that surrounds the nucleus. Most of the atom is empty space. And that comes from the observation that most of the alpha particles went straight through. Some of the alpha particles did what? Some of them didn't go straight through. Some of the alpha particles deflected. So they went through, but they changed direction. What did that tell us? That dime in the middle of the football field, that really, really small dime in the middle of the football field, must be positively charged, okay? There's a small positive nucleus in the middle of the field. Notice we didn't say anything about heavy yet. Okay, just the fact that they caused particles to be deflected didn't say anything about the mass or the density of this nucleus. The third observation, a few of these alpha particles did what? They bounced back. And what did that tell us? Well, we already have the nucleus, right? It's small and it's positive. Now we know the nucleus is dense. It's heavy, right? Because if it wasn't, then these relatively heavy particles, these alpha particles that were fired at it and striking it, wouldn't bounce back. They just knock the nucleus out, and they'd then go pretty much straight through. Let's take a quick look at this one. The students attempt to determine the nature of an object that is hidden beneath a sheet of plywood while rolling marbles under the plywood. Isn't that kind of like blindfolding a bunch of people, putting them beside a football field and letting them run across? This exercise would help students appreciate the difficulties encountered by Compton Einstein, Rutherford, or Thomson? Which one would it be? Rutherford in his work on the nucleus of the atom, right? We want to see what's underneath this piece of plywood, even though we can't actually see it. We roll marbles through and we see what happens to the marbles. So we're indirectly observing, just like we were indirectly observing what was in the middle of the football field yesterday, okay, by sending people one at a time across the football field, just like Rutherford and his assistants did when they fired alpha particles at this gold foil. All right, the Bohr model of the atom, the three aspects to the Bohr model of the atom that separated it from the Rutherford planetary model of the atom. Bottom line is this, all three of these things that differentiate the Bohr model from the Rutherford model, all relate to what? Electrons, yes, electron levels, right? We have electron levels. Each level is characterized by a specific amount of energy. Okay, each level has a different amount of energy. Just like in our analogy yesterday, each level of the saddle dome has a different amount of energy. Okay? The second aspect was this idea that we called stationary states. Electrons orbit around the nucleus. They do what as they orbit around the nucleus? They accelerate. What kind of acceleration is it? Centripetal. Which way is it directed? Toward the nucleus, toward the center of the circle. Is it speeding up? Is it slowing down? But it's still accelerating because it's changing direction. Maxwell said accelerating charged particles generate electromagnetic radiation. Accelerating charged particles generate EMR. But this doesn't. How do we know that it doesn't? Just because we can't see the EMR produced doesn't mean that it's not there. How do we know that it doesn't produce EMR? Yeah. If the electron gave off energy in the form of EMR, okay, if it loses energy, it's going to spiral into the nucleus. It's going to collapse into the nucleus, just like the keys are right now as they swing around my finger, collapsing into my finger. That doesn't happen. It doesn't happen. So it's as if these electrons aren't obeying the laws that Maxwell had figured out, okay, these laws of electromagnetism. It's as if these electrons aren't accelerating. It's as if they're stationary. It's as if they're not even moving. Now, the third aspect that separated it was the idea of electron transitions. Electrons can jump to a higher level. They can also fall to a lower level. When they jump to a higher level, what happens? They absorb energy. And usually, what form is that energy in? EMR, usually. Doesn't have to be, but it's usually EMR. Infrared, visible light, ultraviolet. When they fall, what happens? They emit energy, and it's going to be in the form of EMR. Infrared, visible light, ultraviolet, occasionally an X-ray if it's a really, really big transition, but not usually, okay? Usually just those three. They absorb EMR, they emit EMR. And when they absorb EMR and emit EMR, we can see something like this, okay? We can see spectra. The first diagram that we see there is a reference diagram. When we have a heated solid or a heated liquid or a heated gas under a high pressure, then that's going to emit all kinds of EMR, independent of electron transitions. Okay, it's going to go emit all kinds of EMR, white light, basically. If we separate that white light, then we get a continuous spectrum, all the colors of the rainbow kind of transitioning from one to the other. Okay, that's our reference diagram. Now, the second diagram doesn't look a lot different in the way that it's set up, but the results do look different. This time we have a hot gas under a low pressure. Okay, it emits EMR as well, but it doesn't emit all kinds of EMR. It's emitting specific frequencies, each frequency corresponding to a specific transition that's taken place. So if you get an electron transitioning from level 3 to level 2, then you're going to get a photon produced. Okay, that photon will show up in this emission spectrum right here. You get another transition taking place, you're going to get another photon produced, and it's going to show up there, and so on. So that you get all these different lines on this emission spectrum produced, each corresponding to a different transition from a high level to a lower level. So if you take a look at the second spectrum versus the first spectrum, dramatically different in the sense that this is continuous, this is not, but similar in the sense that we still have red and yellow and green and blue. We still have different colors, and they correspond to something on the continuous spectrum. If you look at the third diagram, when do we get an absorption spectrum? Well, when we have a source of white light. We have to have all the colors of the rainbow in order to absorb colors. Okay? If we take away this source, what is this cold gas going to do? Nothing. It's got nothing to absorb. Okay, if we reintroduce this solid or hot liquid or hot gas under high pressure, and we allow it to produce all the colors of the rainbow again, as we send it through the cold gas, electrons in the cold gas will absorb some of those photons. So now what you get on the other side is the continuous spectrum minus, right? It's a dark spot because you're now missing a red line. It corresponded to a red line that was absorbed by the cold gas. Okay, a red photon that was absorbed by the cold gas. You're also missing a yellow photon. It's dark now because the yellow photon's gone. Corresponds to a yellow photon that was absorbed by the cold gas, and so on. Okay, does that make sense? The final thing we looked at there yesterday was the idea that we can identify elements based on the spectra, the emission spectrum or the absorption spectrum, right? We know that this is very unique. I don't know what element this is, but I know it's unique to a specific element. We know that since this is the exact opposite, it's got to be the same element, same transitions except in reverse taking place. Yeah. That's a good question. Based solely off of spectrum, yes. Based solely off of visible light spectrum, I wouldn't want to go there and try to answer that question because there are usually 3, potentially 4 different types of EMR produced in different transitions. I wouldn't want to suggest that, element number, 106 is going to be all visible light in that spectrum. Okay, could be infrared, could be ultraviolet, could even be X-rays. So I don't know. I don't know the answer to that question. My guess is that visible light would be involved in each of them, but I don't know about if that would be enough. Okay, see a picture up on the board now. This is what we call an energy level diagram. What does that represent? Wow. An energy level diagram shows us, first of all, different energy levels that electrons can be on in a particular atom. This is for hydrogen. Although they all look pretty much the same, except the numbers on the left-hand side might be a little bit different. The nucleus would be down here, right? The protons and neutrons would be down here. And then this would be the first level that electrons can exist on. Second level, third level, fourth level. What do you notice about the spacing of these lines? They get closer together. There are more than 6 lines. There can be 7, 8, 9, 10, 38,142. The problem is we can't keep drawing them in because they keep getting closer and closer together, which means it physically becomes difficult to draw more lines. Okay, does that make sense? We're not stopping at 6 because that's all that's there. We're stopping at 6 because we don't have any more room to draw them. Then we draw in here the infinite level. What does that mean? It's a free electron. The electron's left. It's become ionized. The electron's left the atom. So we've got all these different energy levels. They get closer and closer together as the electron leaves. It gets closer and closer and closer to leaving the atom. First level, we sometimes call the ground state. The rest of them are excited states. And then, of course, in the infinite level, we have the free electron. What you notice on the left-hand side is a bunch of different energies, ranging from neg 13.6 electron volts all the way up to neg 0.38 electron volts, and on the infinite level, when the electron has left the atom, 0 electron volts. What do you notice about those energies? Sorry? They're negative. That seems kind of odd, doesn't it? The energies are negative. I'll give you a little analogy. Okay, answer this question for me, please. What is your potential energy right now? Your gravitational potential energy. We're not talking about gravitational potential energy here, right? But we're talking about potential energy. What is your gravitational potential energy right now? Yep. No, because we always make that a positive 9.8 when we're finding the energy there. Your energy would be, regardless of whether we made it negative or positive, your energy right now relative to the ground would be 0. Yeah. So let's draw a quick little picture of the Earth there. Here's the core of the Earth, right? Here's the core of the Earth. You're standing on the surface. You're standing on the surface. Your energy is 0 joules. Let's dig a hole. Okay, let's go down into the Earth, and let's climb down the ladder. My energy right here at this level is going to be what? -5? Negative something, right? What's it going to be as I climb further down? -12? As I climb further down, it gets bigger, but in the negative direction. If we define our 0 point as when you've left the Earth and you're on the surface of the Earth, then anything as you get closer to the core of the Earth becomes a negative potential energy, right? That's the same thing here. If we define 0 as when the electron has left the atom, when it's on the infinite level, then anything closer to the nucleus is going to be a negative value. You don't get bogged down by that. It's just a convention, right? You don't get bothered by that. The final thing that this shows us is transitions that can take place. You don't need to memorize these names for transitions. I've simply got them labeled there for hydrogen because that's what they are. Okay, that's what they're called. You don't need to know those names. The Lyman series, the Balmer series, the Paschen series, the Brackett series. The Lyman series would correspond to electrons making transitions from any level to the first level, or the other way around. The Balmer series represents transitions from any level to the second level, or the other way around. And the Paschen to the third level, the Brackett to the fourth level, and so on. How do you have this many transitions taking place when you only have one electron in a hydrogen atom? Well, it depends upon where the electron is, what transition is going to take place, right? And where the electron is, what electron it's jumped to is dependent upon what EMR it absorbed. If it absorbs one particular photon, it will jump from here to here. If it absorbs a different photon, then maybe it jumps from here to here. Then it absorbs another photon and it jumps from here to here. Right? So these are possible transitions that can take place within hydrogen. Okay? Not necessarily all of these transitions are taking place within hydrogen. So what are we going to do with this now? Remember, this is for hydrogen. You can see a similar diagram except for different numbers for any element. What are we going to do with this diagram or any other diagram corresponding to another element? Well, there's a couple of questions that we want to try here to show you what we're going to do with it. Using the diagram above, determine how much energy is emitted in the second line of the Balmer series in the hydrogen atom. The second line of the Balmer series in hydrogen. The second line of the Balmer series is this one. And you don't need to remember the Balmer series is this, okay? If the question was phrased like that, then you'd be given the picture, labeled just like it is right there. The second line of the Balmer series goes from -0.85 to negative 3.4. My initial energy is -0.85. My final energy is -3.4 electron volts. Let's find the energy of the transition. We're going to say final minus initial. 3.4 minus 0.85. All right? Minus -0.85. Okay, that gives me negative 2.55. Obviously, if you made it -3.4 minus 0.85, then it's going to not be negative 2.55. So be careful with those negative signs. That's the energy of the transition. That's the energy that's given off when the electron makes that transition. What's it given off in the form of? EMR. So if I wanted to find the frequency of EMR that was given off, I could use the equation E is equal to H over H times lambda. Solve for F. Okay, 2.55 electron volts. Just drop the negative there, by the way. 4.14 electron volt seconds. Calculate a frequency. Even though you're not asked to find that here, you could. And then you could identify what kind of EMR it was. Infrared, visible light, or ultraviolet. Do the same thing for wavelength, right? E is equal to hc over lambda. Okay, word of caution here. Use this diagram. Use the numbers on the left-hand side. Okay, that's the beauty of having one of these diagrams is we know the energy of the levels. But what you don't want to do is use the energy for a specific level. This number, or this number, or this number can never, ever go into this equation or this equation. Those E's always represent what? A difference in energy, a transition that's taking place, not a particular level. Okay, the energy of a photon is never the energy of a level. It's always the energy of a transition. Okay, that's not that hard, is it? Subtracting, right? Subtracting. Although it's like hard grade 5 subtracting, because you have to subtract negative numbers. 2 negatives make it positive, but here's another one. Determine the ionization energy for the electron on the first level. All we have to do is look at the diagram for this. The ionization energy, in other words, the energy required to get it to the infinite level. What's the answer? Quick. 13.6. 0 minus negative 13.6 gives me 13.6. Notice in the first one, it's a negative value, negative 2.55. In the second one, it's a positive value. When electrons fall, it will be negative. When electrons rise, it will be positive. We could find the frequency and wavelength of that as well, right? Finally, page 775 here. How much energy must a hydrogen atom absorb in order for its electron to move from the ground state to 3? Let's look at the diagram. From the ground state to the third level. It's the Lyman series, although it's backwards, because it's absorption. We're going to say neg 1.51 minus negative 13.6. And I think the energy works out to be positive 12.09, I think. Positive because it's rising, absorbing. Right? If you subtract them backwards, you went, I think, 13.6 minus negative 1.51. What's the worst that's going to happen? You get a negative number for that. And you know what? You'll probably get away with that. If you mix them up, you'll probably get away with it. What you won't get away with is if you forget the little negative sign right there. When you subtract them, you still got to include the negative. Okay, whichever way you subtract them. Right? We'll try these two questions, please. I'll copy over the chart so that you can see that. You don't have to keep flipping back. When you finish these questions, your homework for tonight will be these two questions. You'll finish them in class here. In addition, I want you to do worksheet number. This will be the last time this year that I tell you this. I want you to do a worksheet number 26, which will be the very last page in your worksheet booklet.